Here's our usual way of defining a function. So in this case, the name is f. It takes one input, which can be anything, call it x, and the output is x squared plus 3. And let me talk about some different ways we can apply this. So for example, I can do f square brackets 4. That's the most common way, and that plugs in 4 to this formula. Here's another way, and it's important to be aware of these different ways because lots of times when you're reading somebody else's code on the internet, it's going to use different abbreviations for function application. So this is one. So one reason people like this is, imagine I want to do f of 3. So there's some big number, and that looks a lot nicer than f bracket 3. You get the same thing either way, but if you're starting to have like one function applied after another, some big composition of functions, then using this at symbol can be useful. Another way is, and let me do it in a more common type of example. So here I can say front slash matrix form. And I always thought that was some specific symbol that went specifically with matrix form and table form. But it turns out I was wrong about that. And it's actually a very specific, or not a very specific, a very general way of applying a function to some input. Okay, and the only difference between what I did down here on the bottom and what I did here is that for this top one, the function that you're applying comes afterwards. And for this one, the function that you're applying comes first. So the general rule of thumb is that when the actual specific function you're applying is less important, then maybe you use this // notation. So another way I could do it is, here's pi / n. Okay, there it gives me a numerical approximation to pi. And the intuition for when you might choose to use this // version is when the function that you're applying is less important than the input. So here it's really these numbers that are the important thing, and then I'm just changing how is it displayed. How do I display this list of lists? Here pi is really the important thing, and then I'm just saying let's display it as a numerical approximation as opposed to as a Greek letter, pi. So there were 3 different ways to apply this function f. Okay, I guess let me just show you that I could do 7 / f. Okay, and then I get 7 squared plus 3. So there's this // version, there's this at version, and then there's this most common version with the square brackets. Another version that's useful to know is how do you apply a function to every element in a list. So let me remind you what f was. Okay, f of x was 3 plus x squared. Okay, or I could do like zzy, 3 plus zzy squared, where you're supposed to think of this as just some variable name. And so what if I want to apply that to every element in a list? Then I can do / then the at symbol, and now I can give it a list. 2, 1, 10, 1, 2. So this went through and applied f to every element in this list. Okay, that's the exact same as doing table f bracket x for each x in this list here. Okay, so here this is the second type of iterator. So you can see that this one is an abbreviation for this version using the second type of iterator. And let me give maybe a more realistic example. So let me make a list. So random integer, let's say random integers from 1 to 5. And then, so what this is going to tell me is give me a length 10 list of lists, and in each inside list, it's going to be a pair of numbers from 1 to 5. And let's name it something like my list. And I was careful not to use colon equals here because I want this my list to stay steady. So what if I want these pairs? What if I want them to be the center of some disks? So how can I do that? Well, here's one way. I could do disk, and then this is what's called a pure function. So pound is going to stand for the input. And then for the radius, let's just choose a random real number. So by default, that will be between 0 and 1. Okay, and then I want to evaluate this on each of these pairs of numbers. So I want to evaluate this on my list. Okay, so this is what's called a pure function. The pound is the input variable. The and is saying this is where the pure function ends. And now I'm applying it to each element in my list. And so maybe that doesn't look very interesting, but let's make it a little bit more involved. Let's say have a random color corresponding to each of these disks. Hey, so it still doesn't look all that interesting, but let's put it inside of graphics. And to get a better sense of perspective, let's say that axes are shown. And if I wanted to make a longer list, here I could do, say, 30. And there should be 30 disks here. Maybe some of them are covered by bigger disks, but that's an example of using a pure function. Okay, let me show you a more basic way of using pure functions. So say I do pound squared minus 3 ampersand, okay, and then I can apply that to 10. So I get 10 squared minus 3. And this is a useful convention or a useful way of making functions if you don't want to bother naming the function. So notice that here I didn't have to name it. If I wanted to, I could name it. I could say, let's call it G, is pound squared minus 3 ampersand. Okay, and then if I do G bracket 1, I get 1 squared minus 3, I get negative 2. Okay, and that's the exact same as how I'm going to define this function here. Okay, let me call it something else. How about I'll call y, just for a difference. So h bracket y underscore, and that'll be y squared minus 3. Okay, here, because I'm using this formulation of defining a function, I don't put an ampersand at the end. The ampersand only goes together with a pure function, like here with a pound. Okay, and then if I do h of 1, I get the same thing as I got here with g of 1.